So in this session, we will see about how do you represent your graphs. So generally, we have in the last session we have seen how can we what are the terminologies we were using in the graph, and in today's session we will see how do we store the graph in the computer memory. So we can store this graph by means of three ways. One is by means of sequential representation, that is called by using adjacent matrix, and then an adjacent list, and then an adjacent multi-list. So these are three ways where we can use it to represent the graph. So now we will see one by one. The first one is going to be a simple one, an adjacent matrix representation. So now here in this graph, in the given graph, we will see how many vertices are there. 1, 2, 3, 4, 5. So since there are 5 vertices are there, we will take 5 cross 5 matrix. We will take 5 cross 5 matrix. So if there are 6 vertices are there, then we will use 6 cross 6. 4, 4 cross 4. If 3 vertices are there, then we will use 3 cross 3. So simple. If there is there any edge from A to A? Is there any edge from A to A? There is no edge. So it is 0. A to B, there is a edge. 1. A to C, there is a edge. So it is a 1. A to D, there is a edge. It is 1. And A to E, there is no edge. So it is 0. So then A completely we have finished the vertex called A. So we'll go for B. Since it is an undirected graph, so B to A, that's a connection. There is a connection. So it is 1. There is no loop. B to B, there is no loop. So it is 0. B to C, there is no connection. So 0. And then B to D connection, B to E connection. So 1 and 1. So and then C to A, 1. C to B, there is no. So 0. C to C, there is no loop. So 0. C to D, there is a connection 1. C to E, there is no connection 0. For D, the self loop is there. So it is 1. So D to D, the value is 1. D to A, D to B, D to C, D to D, and D to E. So all the vertices are connected, so all are 1. So this is a simple and adjacent matrix representation for undirected graph. Suppose if graph is directed, then we will take only the corresponding outward. For example, A to A, there is no connection. A to B, there is a connection which is going outward, so we will take it. A to C, we will take it. But you can see here, A to D, there is a connection, but is coming inward, so we will not consider. We will not consider. So when for A to D, the value is 0. The value is 0. And A to E, there is no, obviously, there is no connection. So always for data graph in adjacent matrix representation, always we will take only the outward. We will not consider the inward. Always we will consider only the outward directed graphs. Okay, directed edges. This is called an adjacent matrix representation. Okay, so it requires an order of n square in memory, because obviously since we have vertices of 5, then 5 cross 5 is required. So it requires n square in memory. Next one is an adjacent list representation. Straight away we'll go to example. So now here, by means of list, it's a linked list representation only. So now you can see here, there is a B, C, D. So from A, there is a connection to B. So A to B, and then this node address will be mentioned in this place. Okay, like we put it in the linked list, a node. So B is the data, and then the next node is going to be the address of the C node. And then C node address will be mentioned over here, and the C node. So for A, it is having only 2 outputs, to B and to C. So B and C are covered. So there is null address in the last node. Likewise for B, how many outputs are there? To C and to D. So to C, and then from C to it is D. C to this D. So only 2 outputs. So for C, how many outputs? Only 1. So only D. So for D, how many outputs? A and B. So A and B. So for undirected graph, we will consider in the both the directions. We will consider both the in the both the directions. So A to B, A to D, B and D. So for B, so if whereas here we consider only the we consider only the outward, but here we consider both the sides. Okay, we doesn't bother with inward or out. That is the directions, right? So B to A, B to D, and B to C. We will consider everything. So A, C, D. Likewise for remaining everything. Suppose there for some node we have weighted. We have a weighted edges. So we will add one more field for the weighted. So B, and then the corresponding weight between the A to B is 4. And then A to D is 2. So we have added one more field called weighted field. And then there we will represent our the weight of the corresponding edge between the two nodes. So this is how we can represent a graph using adjacent list representation. Next one is multi-list representation. So where in the previous two cases we have represent our graph using an vertex, whereas here we will represent using edges. We will represent using an edges. So multi-list. So edge 1 is between the a node called 0 and 1. So between the 0 and 1. So for 0, it have another side, how many nodes, how many edges are there? The other side, it had to have an E2. For 1, the other side, it have an E3. So corresponding H2 and H3. H2 is for 0 and H3 is for 1. Likewise, H2. H2 is between the 0 and 2. 0 and 2. And then the other side of 0 is going to be edge 1. Edge 1 is already covered. Edge 1 is already covered. There is no need to go back once again. So we will represent null over there. And then here, after a 2, we have an H4. So we have an H4. H4 is yet to be covered. So we have an H4. Likewise, H3 is existing between the 1 and 3. So 1 and 3. So the other side is going to be edge 1. Edge 1 is already covered. So 3. So the 3 other side is going to be, the 3 is other side going to be E4. E4 is yet to cover. Okay, whichever is very much, suppose we in the 3 node, if you consider both the sides E4 and as well as the E5. So then there will be confusion that which one to be taken. So always you take the least edge. So H4 is the least yet to be covered. So we will take the H4. So the H4 is between the 2 and 3. So the other side of 2 is going to be H2. H2 is already covered. And the other side of 3 is going to be H5. So here we will have an H5. And then likewise for H5 and H6. H6 between the 4 and 5. The other side of 4 is going to be H7. So H7 need to be covered. So H7. And then 5. The 5, there is no corresponding inside other edges. So null. And then H7 between the 4 and 6. So all the edges are covered. So null. So this is called multi-list representation. Wherein the matrix or linked list representation, we have taken the vertexes and then we have tried to represent the graph. Where in the multi-list representation, we have taken an edge and then we have tried to represent the graph. This is the difference between the three types of representations in the graphs. Okay, thank you.